Okay, welcome back. We're trying to find the Fourier series coefficients of some signals, and I've got three examples here, XA, XB, and XC. And remember, just a subtle piece of information that we're only dealing with continuous time right now, and we're only dealing with periodic signals. So each one of my examples is continuous, and each one of my examples is periodic. All right, let's start, and let's start with A. So the goal is, if you recall, to write X as a sum of harmonically related complex exponentials, like this, okay? So the first thing we want to do is figure out what is omega 0? What's the fundamental frequency? And so you have to go back and remember about sinusoids, what we said about sinusoids, but it's this number that multiplies t. Remember that cosine of 100t is periodic, and its period is 2 pi over 100, and its frequency is 100. So just by inspection, we can get the fundamental frequency is 100. All right, so that takes care of this guy here. Okay, all that's left is to figure out what the AKs are. How much of each ingredient do we need? Well, from the previous video, we saw that the AKs from the analysis equation is 1 over t, integral of t, xt e to the minus j k omega 0 t dt, right? So that's kind of where we finished in the previous video. And we could use this equation, but for cosines and sines, this equation is not necessary. And that is because, remember, the goal is just to write our function in terms of complex exponentials. And we can actually just use Euler when we're dealing with sines and cosines to break it down very quickly into complex exponentials. Okay, that is to say, xa of t, if I use Euler's equation, cosine is 1/2 e to the j 100t, right, plus 1/2 e to the minus j 100t, right? And so it's already in this form, a sum of complex exponentials. That's exactly the synthesis equation. So it's already in its Fourier series. So just by inspection, we see a 100 up here. So this is the first harmonic. And we see a minus 100 up here. This is the minus first harmonic. Okay, so in other words, this is the k equals 1 term. This is the k equals minus 1 term. All right, so just by inspection, I see that A1 is equal to 1/2. Why is that? Because by definition, A1 is the thing that's multiplying the first harmonic. So the thing that's multiplying the first harmonic is 1/2. And similarly, I look at this. This is the minus first harmonic. The thing that's multiplying the minus first harmonic is also 1/2. So these are the Fourier series coefficients. That's it. There are only two non-zero Fourier series coefficients. And so we'll also point out that AK equals 0 for k not equal to plus or minus 1. Okay, in doing so, we've specified the entire series now. All of the AKs are 0, except A1 is 1/2 and A minus 1 is 1/2. Now, previously we said that these A's can be complex. And so in order to plot complex numbers, we need two plots. Usually the real part or the imaginary part, or the magnitude and the phase, right? So being that these are completely or purely real, I guess we only really need one plot in this example. But usually what we do is we show the magnitude of AKs in their own kind of plot right here. So this would be k equals 0, k equals 1, k equals 2, minus 1, minus 2. And let's plot it. Well, what's the magnitude of 1/2? 1/2, certainly. So we just come up by 1/2. Okay, and notice how I've drawn that bar as a bar, not as with a dot, not a stem plot, but just a bar plot. And this is usually done in Fourier analysis to distinguish between Fourier analysis and plotting a discrete time signal. So we're not going to make a stem plot with a dot up there. We're just going to make a bar. And similarly, the a minus 1 term has a magnitude of 1/2. Okay, and the rest are 0, so that's our magnitude plot. And our phase plot, well, our phase plot is a little ambiguous. And certainly I didn't have to stop at 2, by the way. I could just keep going. These are all 0. Our phase plot is a little ambiguous because our Fourier series coefficients are purely real. And so the phase of a purely real number and a positively purely real number is 0. So they're just a bunch of zeros here. There's no phase. Okay, that's the answer. Now let's move on. Let's see how that compares to the sinusoid, or the sine wave. Okay, and again, because this is a sine wave, I can avoid using the analysis equation and go right to Euler, right to the complex exponentials. So this is 1 over 2j e to the j 100t minus 1 over 2j e to the minus j 100t. Okay, that's Euler's equation. Now, then by inspection, just by inspection, I see that A1 is equal to, remember that's the thing that multiplies the first harmonic. This is the first harmonic. I guess let's back up. Why is this the first harmonic? Because remember we said omega is 100, so this is 100 times 1. So that makes this the first harmonic. This is 100 times minus 1 here. So that makes this the minus first harmonic. K equals 1, k equals minus 1. So now, by inspection, the thing that's multiplying the first harmonic is 1 over 2j. Okay, so that's A1. The thing that's multiplying the minus first harmonic is minus 1 over 2j. And there are no other non-zero Fourier series coefficients. So altogether, that specifies the Fourier series coefficient for the sine wave. And so let's plot magnitude and phase here. So this will be the magnitude of AK. See, and so I've got, let me just put 0, 1, 2, -1, -2. Okay, and what is the magnitude of A1? Well, remember J is a direction. Now think about the complex plane. Go check out those previous videos. The complex plane, this J is a direction. The magnitude of this is 1/2. Okay, and what's the magnitude of -1 over 2j? Well, that's 1/2 as well. Okay, and all the rest have a magnitude of 0. What does the phase of the Fourier series coefficients look like? Well, what's the phase of A1? What's the phase of 1 over 2j? Well, that's negative 90 degrees, or negative pi over 2. Again, if you're uncertain about that, go back to the previous videos about complex numbers. What's the phase of this guy? That's positive pi over 2. You need to get this down. This is not going to go away anytime soon. So again, if you don't know that, you need to fix it now. And then the rest of the AKs are 0. So this is the phase. All right, so we see how the sine and the cosine representations, Fourier series representations, differ a little bit. And you can loosely describe this as follows. The cosine has half of its energy in the minus first harmonic and half of its energy in the first harmonic. And both harmonics are in phase with one another. That's the hallmark or the fingerprint of a cosine. The sine wave has half of its energy in the minus first harmonic and half of its energy in the first harmonic, just like the cosine. However, the sine wave has its first and minus first harmonics out of phase by pi with one another, because one goes to the right, pi over 2, and the other one goes to the left, pi over 2. So its harmonics are out of phase by pi, and they're each out of phase by pi over 2 relative to the cosine. This is the hallmark of a sine wave. All right. Now, example C. Again, I have sines and cosines. But first we have to understand what's the fundamental frequency of this thing. I have 100, I have 100, I have 200. Well, you got to go back to the video on fundamental frequency. So this guy repeats every 2 pi over 100 seconds, or if you want to think of seconds. This guy repeats every 2 pi over 200. So what's the lowest common or the least common multiple? And that would be this one, right? Or no, excuse me, this one here. And this is twice that one. So this is the least common multiple, and that means it's the fundamental frequency is 2 pi is 200. No, I'm sorry. Let me back up. This guy has a frequency of 100, right? So its period is 2 pi over 100. The same with this guy. This guy has a frequency of 200, so it has a period of 2 pi over 200, half this one. So this goes through 2 cycles every time this one repeats. So we have to wait this long for the slower ones to repeat, and when the slower ones repeat, the faster one has gone twice, but it's ready to repeat also. So go back to the least common multiple idea with the fundamental frequency video, but the fundamental frequency here is 100. Okay, so that makes this guy the first harmonic, right? It's got the first harmonic component. This one has a first harmonic component, and this one is twice that. So that's the second harmonic, and this one, the constant, that's the 0th harmonic. That's the DC term, or the constant value. Okay, so again, being that we're dealing with sines and cosines, we can express this using Euler's equation. So this is 1 plus 1 over j2 e to the j 100t minus 1 over j2 e to the minus j 100t, right? That's the sine. Then the cosine is 1 over 2 times e to the j 100, but we have that 2 out in front, so that just makes e to the j 100t plus e to the minus j 100t. And then we have the cosine of this thing, so this is plus 1 over 2 times e to the j 200t plus pi over 4 plus 1/2 e to the minus j 200t plus pi over 4. So this is what we're dealing with now. And so we've already decided that our fundamental frequency is 100. So here I see a first harmonic, right? Because this is 100 times 1. But here I also see the first harmonic. So I have to group those together. So I'm going to write my signal like this. 1, that's the 0th harmonic, plus 1 plus 1 plus 1 over j2 times e to the j 100t, right? Then I see I've got the minus first harmonic here because 100 is being multiplied by minus 1, and I have a minus 1 harmonic there. So I'm going to group those together. Plus 1 minus 1 over j2 e to the minus j 100t. Okay, now I'm going to use properties of exponents for the remaining two terms, and I'm going to write this as 1 over 2 times e to the j pi over 4 e to the j 200t. Okay, that's the first, or the second to the last term, that one. Then plus 1/2 e to the minus j pi over 4 e to the minus j 200t, like this. Now, e to the j pi over 4, that, if you find this in the complex plane, is the square root of 2 comma square root of 2. So this thing here is square root of 2 over 4 because of the 1/2 plus the square root of 2 over 4j. And this thing here, if you find e to the minus j pi over 4 in the complex plane, right, that is square root of 2 over 2 comma minus square root of 2 over 2, and then we have the 1/2. So this is square root of 2 over 4 minus square root of 2 over 4j. All right. Let me make some room. So now, by inspection, I see, well, this is the A0 term here, right? In other words, this is times e to the 0, k is 0. So by inspection, I see that A0 is equal to 1. Now, this guy, this is the k equals 1 term because, again, the fundamental frequency is 100, so k equals 1. And so I get A1 is equal to 1 plus 1 over j2. And then here's minus 100, so this is the k equals minus 1 term, and this is A minus 1. And notice, this is the complex conjugate. of a minus 1, right? Then I look at a2, right? Because this is a 200 in the power here, and that's 100 times 2, so this is the k equals 2 term. So the coefficient out in front is this guy in orange. Square root of 2 over 4 plus j square root of 2 over 4. And then I look over at this term, and here's the minus second harmonic, because this is minus 2 times 100. See, it's all relative to this guy. So this is minus 2 times 100, so in green that's the coefficient, and notice that's the complex conjugate of what I just wrote down. Okay, and then all the other AKs are 0, so I'm going to write that down. AK equals 0 when k does not equal 0, plus minus 1, plus or minus 2. So all of those things together specify the Fourier series of our wave. All right, now let's plot the magnitude and the phase. Okay, this will be the magnitude plot. Okay, so what's the magnitude of 1? Well, that's 1. All right, A1. So this is where k equals 1. What's the magnitude of 1 plus 1 over j2? Well, the magnitude of A1 is the square root of 1 squared plus 1/2 squared. So 1/2 squared is 1/4. 1 is 4/4, so this is the square root of 5/4. Square root of 5 over 2. Okay, square root of 5 over 2. Like this. All right, now notice, okay, the minus 1 term has the complex conjugate. This was a minus sign. But that doesn't change, so we just put a minus there, but that doesn't change the magnitude taking the complex conjugate, right? Because we square the minus, and it still makes square root of 5 over 2. Now A2, what's the magnitude of A2? That would be the square root of the square root of 4 squared plus the square root of 4, square root of 2 over 4 squared. So this would make 2 over 16, or 1/8, and 1/8 is 2/8, 1/4, so this looks like it's 1/2, if I've done that correctly. So here's 1/2, here's 1/2, and then the rest are 0. Okay, and finally, just to completely specify this thing, let's plot the phase of AK. All right. So what's the phase of A0? Well, the phase of a real positive number is 0. Think about where this thing falls on the complex plane, what angle it makes with the positive real axis. All right, now A1, 1 plus 1 over J2. Well, that one's a little interesting, but we can use trig identities and so forth, and we would take the inverse tangent of 1/2 over 1. Okay, and we'll just leave it like that. Inverse tangent of 1/2. In other words, the y, or the imaginary part, over the real part. Okay, and then when we take the no, the imaginary part, excuse me. The imaginary part is, the j's in the denominator there. So the imaginary part is actually minus. So that should go down, I believe. Let me... minus the inverse tangent of 1/2. Okay, because the tangent is an odd function, so I can pull out the inverse, or the minus. And then the complex conjugate turns that minus then into a positive, so this is the inverse tangent of 1/2. Okay, now I'm on to A2, so I need the angle of this guy, so that would be the angle of A2 is equal to the inverse tangent of the square root of 2 over 4 over the square root of 2 over 4. So do you know what that one is? Equal parts right and equal parts up. That's 45 degrees, pi over 4. Okay, and A minus 2 is the complex conjugate of that. So the angle of A minus 2 would be minus the inverse tangent of 1, basically. So that would be this guy, minus pi over 4. And the rest are 0.